Okay, friends, Saturday, 8:30 p.m. in Indian Standard Time. We are all here for the Saturday Manufacturing Talks. Saturday Manufacturing Talks is a mega webinar series started in the month of March 2021. So every Saturday, 8:30 p.m., we all assemble here to listen to the great speakers from academics, from industry, talking their experience, sharing their experience in the field of manufacturing. The Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur is an interdisciplinary industry-focused R&D center. We have established this center early 2018, working closely with the industries, both public sector and then private sectors. We are working following the footprints of Warwick Manufacturing Group in the UK. We are visiting to work on the modern concepts so that we can bring innovations in the field of manufacturing. At the same time, we'd like to create an ecosystem between the large industries, small industries, academic institutes, and also the research the units. We are very much open to work with the international expertise as well. While executing the projects for the big industries, we are also giving training to industry professionals in the field of the manufacturing. So we are getting the problem statements from the OEMs, working closely with the OEM engineers and then researchers, giving solutions to them. And at the same time, we are nurturing the MSMEs, micro, small, medium, and enterprises, so that they can also get to know the modern concepts and they can be in the supply chain for the big industries. While executing the projects for the big industries, we are filing patents. That means the intellectual property rights are also jointly shared. We do have the large number of equipment, state-of-the-art facilities, so that we can work for the industries. And our facilities are the industrial scale, so that we can catapult the academic innovation into the manufacturing industry's need. So these are some of the examples of the facilities that we have, pictures of those facilities, the hybrid additive manufacturing facility, which can print the metal objects close to 1 meter length. We do have the scanners. CT scan machine is also going to come up, which should be able to scan large size objects. Then apart from that, the several others, the machining centers, the characterization facilities. And in addition to that, the large number of the robotic welding facility. They are all sensor integrated, so we can check the product quality. And at the same time, we can also check what is the health of the machine. We do have the MIG welding facility, TIG welding, spot welding, laser welding, friction stir welding, and also the robotic structural vibration, the facility. All our infrastructures are housed in the 40,000 square feet, the industrial, the said in the area. I'm just showing a small video of that. We are very much eager to work with the industries. So on daily basis, we are in the interactions of the various types of industries so that they can come forward and we can also work for them. With this small introduction of the Center of Excellence, now I'd like to request my colleague, Professor Anandaroop Bhattacharya, to introduce Professor Christopher Bailey and to take the proceedings. Yeah.
Thank you, Professor Pal, and for giving the introduction to both the Center of Excellence in Advanced Manufacturing Technologies at IIT Kharagpur, as well as about the Saturday Manufacturing Talk webinar series. So it's my great pleasure today to introduce the speaker, whom I have known for, personally for last 4 or 5 years, but even before that, I have known him based on his work and his eminence across the world for many, many years. It's my great pleasure today to welcome and introduce the speaker for the day, Professor Christopher Bailey, or Chris Bailey. Professor Bailey is one of the most eminent researchers in the area of electronic packaging and manufacturing across the world. He's a global stalwart, and anybody who is related to or who works in this domain knows him right away. He is the director of the Computational Mechanics and Reliability Group at the University of Greenwich in UK. He has a PhD in computational modeling and an MBA in technology management. Over his illustrious career so far, he has published over 300 papers on design and simulation of electronics packages. Chris has served on several external government committees, which include the 2014 UK Research Excellence Framework to assess research outputs and research impact across UK universities. He is also a member of the EPSRC College and has been an associate editor for the IEEE Transactions on Components, Packaging and Manufacturing Technologies for many years. He also plays a very pivotal and important role in the overall electronic packaging ecosystem across the world. He currently co-chairs the Modeling and Simulation Technical Working Group on the IEEE Heterogeneous Integration Roadmap. This is the roadmap, HIR. This is the new roadmap in the domain of electronics packaging, which replaces the erstwhile SIA roadmap. Okay. Professor Bailey also, as I said, is very well known. He has lots of contributions in the overall ecosystem, and especially as part of IEEE, being currently the junior past president of IEEE Electronics Packaging Society, which means he was the president last year of IEEE Electronics Packaging Society. So that's the status of the person whom we are going to listen to today. And with IIT Kharagpur, Professor Bailey is a good friend of us. He has a relation now for almost 5 years. He visited us in 2018, and he has been one of my mentors based on whose mentorship and guidance I started some of the research activities, as well as offering the course on fundamentals of electronics packaging as an elective at IIT Kharagpur. Today, the course has, he gave a few lectures in the first time, during the first time that I offered the course in 2018. And today, the course has really grown, and several of the students of the current batch are actually there today in the audience. They're all very eager to listen to Professor Chris Bailey. So without further ado, I would really now invite Professor Bailey to start his presentation. Thank you.
Thank you very much, Anand, for the very kind introduction. I'm just going to now share my screen. Anand, is the screen clear?
Yeah.
Excellent. Well, thank you. And again, thank you very much for the introduction. And may I say thank you also for the invitation to present at this meeting. This talk will build upon the presentation given last week by Professor Bhattacharya on electronics packaging. I'm going to talk about what we call advanced packaging, but also additive manufacturing, and how additive manufacturing is now adding value to electronics packaging. As Professor Bhattacharya mentioned, I'm at the University of Greenwich. I have been at Greenwich since 1991, 30 years experience working in electronics packaging. both on UK, US and EU funded projects, as well as working quite closely with industry partners in Europe and in the UK. Much of the work I do is understanding the physics of what drives failure in electronics packaging, i.e., for example, solder joints or die attach material. And why do they fail, and how can we mitigate those failures using design, modeling, and simulation technologies, what we call virtual prototyping. I have also been very active, as Professor Bhattacharya mentioned, with the IEEE Electronics Packaging Society. And this is a worldwide society, and as Anand mentioned, it now has a technology roadmap for packaging going forward. So here is my university, the University of Greenwich. For those who have been to London, this is the River Thames here, and Greenwich is quite famous for its maritime history, but the University of Greenwich is based at the campus in Greenwich itself, as well as in Chatham, which is in Kent, where most of our engineering laboratories are. I run a research group. I've been head of this research group since 2004. And our research mission is very much in the area of modeling and simulation and materials characterization and failure analysis of electronic packages, as well as advanced packaging. And I'll talk about some of these projects in a moment. So the contents of my talk today, as per the title of the talk, is very much around advanced packaging. What do we mean by that? And also the very exciting field of additive manufacturing, and how is that adding value today to electronics packaging? And then I would like to make some conclusions. You may have heard of Moore's Law last week. Traditionally, since the 1960s, what has driven the electronics industry has been Moore's Law, which is based on transistor scaling. So Moore's Law is that the number of transistors on a piece of silicon would double every 18 months. And that has held true since the 1960s until recently, because Moore's Law was also about the economics of this scaling, and today the actual economics changed nearly 10 years ago, and it started to become much more expensive now to continue Moore's Law. And if we think about where Moore's Law has gotten us today, down at 5 nanometer dimensions, the transistor sort of scaling that we have achieved, which has just been incredible as how that's developed and progressed consistently over many years. But today, the sheer cost of continuing Moore's Law and what we call system on chip, where you try to build as much electronic functionality on a single die, the cost of doing this going forward has become too expensive. And hence packaging and advanced packaging is now seen as the way forward by many companies in the industry, including the likes of TSMC, the world's largest fab facility, as well as Intel. And just to come back to the issue of cost, this is actually the cost for design. And what we are looking at here is the scaling from 28 nanometers down to 7, down to 5. And this is in millions of dollars. This is just the design. costs. So hence this incredible exponential growth in the cost of following Moore's law and system on chip type integration. Today, we hear a lot about the term chiplets. So if we can imagine system on chip with a lot of different functionality, we can now start splitting this functionality. And it's what's known as disintegration. So going back to single die, but if you had logic and RF capabilities, say at different technology scaling, why would you do that all on the same die? You can actually start bringing these together now in a package. And this is known as system in package, as compared to system on chip. So this is the chiplet evolution, and how we package different chiplets from different technology nodes together is the whole concept of system in package, and also heterogeneous integration, where we may wish to pull MEMS components with optical die all in the same package as well as silicon. So I mentioned that term heterogeneous integration, and as Professor Bhattacharya on the introduction, he mentioned this roadmap, the heterogeneous integration roadmap. I will talk a bit more about that shortly, but what do we mean by heterogeneous integration? It is the integration of different technology nodes, 28 nanometers, 7 nanometers, 40 nanometers. We use the technology that is best for the die that we're producing. And that could be MEMS, silicon photonics, power ICs, logic, RF, etc. It is miniaturized in the package by advanced packaging technologies. It's performance optimized in terms of electrical behavior, signal and power integrity, as well as thermal and mechanical. So advanced packaging architectures, I think last week you would have heard about flip chip and BGAs and through-hole technologies. Here we're looking at packaging, wafer level packaging, fan in and fan outs. Now this is actually doing the packaging on the wafer before you split the die on the wafer. You would actually package on the wafer, and two common technologies there is fan in and fan out. And what we mean by fan in and fan out is how the redistribution layer from the die is whether it fans into the interconnects or it fans out to interconnects that are placed underneath the die. Then we have flip chip. You would have heard about that last week. And 3D IC. Now this is actually taking different die and stacking these on top of each other. This is very common today in memory, where we actually stack the die and then we use what's known as through silicon via technology to interconnect the die through each other. Now all of these would be looking at a substrate or an interposer, where you can have the different die in the same package but connected to each other and the outside world through an interposer. When we're pulling together different die technologies all in the same package, as I mentioned before, this is system in package. And also we're seeing quite a lot happening today in embedded die, where in the substrate or the printed circuit board, you're actually embedding the die inside those. You would have heard last week about different interconnect technologies, and of course interconnect here with these different type of architectures is very important. This could be through bumping, copper pillars, studs. I did mention through silicon vias for stacked die, bumpless, and obviously embedded technologies. So this is a high level picture of advanced packaging today. And this is a field of much research and development, both in universities and in industry. So how is the packaging area growing? This is looking out to 2030, and I mentioned above QFN type packages. I'll talk a little bit more about those in a moment. You would have heard last week about traditional lead frame type packages. They are sort of remaining constant. This here is the number of billions of units, billions of packages produced every year, but we can see the growth in different packaging technologies. And as I mentioned before, we're moving away from that system on chip towards system in package using different technologies like these. If you are interested in learning more about advanced packaging and heterogeneous integration, do go to this link here on the IEEE Electronics Packaging Society webpage. There are 23 chapters in this roadmap, and each of these chapters discusses the current state of the art in different areas of heterogeneous integration and advanced packaging, and also the challenges and potential solutions to those challenges going forward. So it covers a whole number of application areas, as well as technologies and underpinning technologies for advanced packaging, such as modeling and simulation, and also co-design, which I'll talk a little bit more about in a moment. So coming on to the design, you would have, that chart I showed above about the sheer cost of design for packaging, but taking a high level view of design today, essentially we have chip design, and it doesn't integrate that well with package design and then the overall board design, the whole overall printed circuit board, or the system as we may wish to call that. And generally there'll be different tools, design tools used in each of these. So we can think about Cadence, Mentor Graphics, and the different tool sets that are used. For advanced packaging technologies, where you have a whole number of different die in the same package, not a single die, but many different die in the same package, you need integration between these tools. So that will become important for the future, this co-design, as we call this, integrating the design flow from chip to system. And also today, electrical analysis, thermal and mechanical tend to be done in different tools. In the future, multi-physics for advanced packaging and heterogeneous integration will be very important. These are some of the trends and challenges that we need to see happen to enable new innovations in advanced packaging and heterogeneous integration. Coming back to the roadmap, if you are interested in learning more about what's happening here, there are these two chapters in the roadmap that you can read more on this. The whole area of multi-physics for advanced packaging is really understanding the interactions, the electrothermal interactions, the thermomechanical interactions, particularly chip package interactions, and the influence of the package design on the electrical performance of the chip is becoming quite important. So the tools that are evolving from the tool vendors are starting to address some of these challenges here in the area of multi-physics and scale modeling domains. Let me now move on to some examples, and this is actually a QFM package. I've picked this example here because understanding the package design and behavior is important, but also understanding the influence of the assembly process. You know, what materials are we using on the board when we assemble a package on the board? And this is the area of conformal coatings. Now, conformal coatings are placed on a printed circuit board with the packages, and it's there to protect against contamination, moisture, and corrosion, and also a mitigation against a phenomena known as tin whiskers. Now, over the last 15 years, the industry has moved away from tin lead solder and solder finishes towards high tin content. So this is under environmental legislation where we've had to remove lead from the solder materials and go towards high tin materials. But that can evolve in this phenomenon known as tin whiskers, which is a failure mechanism that we need to avoid. And in doing that, the industry would use something called conformal coatings. But when we use conformal coatings, how does it interact with the package? So this is a project we did at Greenwich with a number of companies, looking at different package types. And when we're looking at these packages, it's very important to understand the architecture of the package and using characterization technologies like CT tomography to really understand what the makeup and the architecture of a package is. And then we would use finite element type techniques to understand how this package and the conformal coatings on a board would interact. And in the industry, in understanding how a package would behave when you switch the package on, i.e. the electronic product's been switched on, when it switches off, we assess that behavior and the impact of that behavior on reliability, thermomechanical reliability, through thermal cycling testing. So here you can see different conformal coatings that will have different material properties, and we would use finite element models to understand how this domain behaves thermomechanically and the impact of that on subsequent reliability. And here's some results here where we've investigated different coatings, no coating on different package types. And what was very important here is the material properties and the glass transition temperature of some of these conformal coatings. Because what we have here with the package and the printed circuit board is what we call a CTE mismatch, a coefficient of thermal expansion mismatch between the materials. And understanding the influence of that mismatch and the properties of the coatings that will be surrounding the package here, it's very important. Now, you could do lots of testing in this type of domain, but accurate simulation and modeling tools really does provide an insight as to how the conformal coatings would interact with the package. So my message there is that understanding how packages are assembled to printed circuit boards and the materials that you're using is very important in terms of reliability. This example here is where we are stacking two dies, and this is for a focal plane array using indium solder bumps. And these are a lot of interconnects, 1280 by 1024, and it's very fine pitch assembly. So here we were looking at a bonding technology known as thermosonic bonding, where we are actually taking what's known as the silicon readout IC to this compound semiconductor, which will have a pixel array on there. So this is a very fine pitch flip chip type interconnect, but flip chip in one die onto another die. So it's a stacked die system, which is an advanced package. And here we were looking at and investigating for our industrial partners, what would be the influence if we did reflow soldering for this, or thermocompression bonding in terms of the quality of the joints and also warpage in the package assembly. I talked about wafer level packaging, and this is where you're actually doing the packaging on the wafer. And here we have the redistribution layer. So there's the package. The redistribution layer here is a fan out package. So this is a wafer level package, but also another die is bonded on the underside here. And this example here shows how important the properties of the mold compound are in terms of the thermomechanical behavior of this die assembly. And you can see here, depending on the molding compound used, we have different levels of solder damage and also different levels of stress in the die. Another challenge for advanced packaging is the very small interconnects that we have in advanced packaging, and the high current densities that could be imposed on those interconnects. So a phenomenon known as metal migration or electromigration, but it's not just electromigration, it's also thermal and mechanical. So it is a highly multi-physics problem, and you need multi-physics simulation type tools to understand the influence of electromigration plus thermal migration plus stress migration on these types of interconnects. And today we hear tremendous amounts of interest in machine learning. And in advanced packaging and in electronics packaging in general, we are gathering huge amounts of data from our manufacturing processes and our qualification processes. How can we use that data effectively using machine learning algorithms? What can we learn from that data? So we are seeing a lot of interest today in using machine learning and AI in understanding our products. And in this example here, we were using machine learning to understand how similar one particular package would be to another in terms of its reliability. Looking at the challenges for advanced packaging, in terms of the design tools, co-design, very important. Chip, package, and board system integration of the design flows. Also multi-physics, those interactions between electrical, thermal, and mechanical, and also sharing models through the supply chain. And how do we do that without divulging intellectual property? It is becoming quite important. Metrology and modeling, I've given some examples above on that, very important. Machine learning, and with advanced packaging and heterogeneous integration, we are looking at different package architectures, the system in package I mentioned before, but also new materials, new interconnect structures. What are their failure modes and what are their failure mechanisms? Okay, I'd like now to move on to additive manufacturing. Now, additive manufacturing has been with us since the early 1980s, and back then 3D systems, Chuck Hull here, who developed stereolithography. The key thing with additive manufacturing is all digitally driven. So we start with our CAD models and we go through different steps here to actually start forming our final 3D printed part. One of the exciting things with additive manufacturing is that the design flexibilities and the design freedom it allows engineers compared to subtractive manufacturing. And I'll talk a little bit more about that in a moment. This is a classification of different additive manufacturing technologies. You can find more about this at the website link here. But metal extrusion, jetting, inkjet is particularly important for electronics packaging, powder bed fusion, binder jetting, sheet lamination. So there are many terms in the additive manufacturing world that are used by different companies and organizations for their technology. But when you look at them closely, you can classify those under one of these 7 headings. Additive manufacturing is very much digitally driven, and there is huge interest from the software tool vendors in using their technologies, their software technologies in the additive manufacturing domain. And you can see a whole number of tools here going down to the simulation tools here, such as ANSYS, but then CAD design, processing, workflows, quality assurance, security. So a huge market for the tool vendors. Additive electronics. Now this is bringing together electronic packaging and additive manufacturing. And this is a chart here from the heterogeneous integration, chapter 8, the roadmap. But here we're showing where you can, for a package here, where different type of printing technologies and additive manufacturing technologies can be used in the electronic package, in fabricating that package. So this term additive electronics is becoming quite popular today, and it is merging packaging with additive manufacturing. This technology here is known as a jetting technology, aerosol jets. Of course, with additive manufacturing, when we look at this, how close can we get to the resolutions that we would get through traditional technologies? But this is providing the capability to actually print over 3D surfaces. So you can see this type of package here with these interconnects that were actually printed through this aerosol jet system. Nano dimension. Now this is a commercial printer that is printing printed circuit boards, flex or FR4 type boards here, and then placing components on these. But these are the sort of, it would, you know, the capability here is a build size of 20 by 20 centimeters. And then we're looking at different trace sizes and dimensions for the interconnects. But printers like this to print circuit boards, but also possibly to place the components and embed the components as well, is becoming popular today. That's a commercial printer. This is a European project that I participated on a couple of years ago that was looking at bringing together 3D printing and 3D assembly. And here we were working with a robotics group at the IPA Fraunhofer Institute. So the next factory process, there's just some capabilities here, but most importantly, just let me bring this up, that this was sort of a plug and play system where you actually had the printing units, curing or sintering of the materials, assembly of the components, and then inspection. So boards would go back and forward here as the 3D printing process took place. modeling and simulation for additive manufacturing in electronics packaging. One of the key things is as you build layer by layer, you will get thermal stresses, and understanding those is very important. This is an example here of where we're comparing a standard circuit board to an inkjet printed circuit board using silver as the conductive material instead of copper and acrylic instead of FR4. And what we were looking at here, again, in predicting this behavior, this thermomechanical behavior, as you build up the layers, and what you have in the printing process is cure shrinkage as well as CTE behavior. And just to highlight here that the models that were built here helped us understand the difference between standard materials and inkjet printed materials. The stresses were pretty much the same, but the deformation in the inkjet printed materials was much higher than you would have had in standard materials. So here we're looking at design tools, modeling to help understand and optimize the 3D printing process for the printing of circuit boards and package components. Here's an example here from Mentor Graphics, and you would remember I mentioned this design freedom that 3D printing enables. This is a traditional heat sink that's been extruded. This is a comparable additively designed heat sink. It's just that additive manufacturing gives you this type of design flexibility that you could not produce using traditional subtractive parts. And here is another example of heat sink optimization using modeling and simulation technologies, parametric optimization and topological optimization, where, of course, for a heat sink, it is to remove as much heat from the die and the package as possible. But using modeling with the objective of using additive manufacturing, you can design some very interesting structures that will maximize the heat removal from our systems. So the challenges for additive manufacturing, there's a lot of research taking place today in the area of electronics packaging. But the challenges are the materials, the fabrication speed, the dimensions and tolerances, and also the evolving design tools. So I'd like to now conclude my presentation. I talked about Moore's law and the cost of continuing Moore's law for system-on-chip technologies. The economics of Moore's law does not work anymore. That is well understood. So future scaling that we have seen with Moore's law is going to be through heterogeneous integration. And there is a term used in the community called more than Moore. Through heterogeneous integration and advanced packaging, we could probably do better than Moore's law going forward. So with chiplets and advanced packaging technologies, there's some very exciting opportunities ahead. Additive manufacturing is now being used, and there's a lot of interest in this, in the area of electronics packaging in general. I did focus this talk around some of the code design and multi-physics modeling challenges. Very important technologies, because understanding reliability or electrical thermal behavior of our electronic parts and products and packages at the early concept stage is very important. Identifying an error here or a design flaw can save significant costs later, because these costs of not capturing a design flaw early dramatically increase over time. I talked about the heterogeneous integration roadmap. Please go to the website link if you're interested in reading more about what's happening in this exciting area. And finally, I'd just like to talk about a collaboration that I am starting, and I'm delighted to be starting this collaboration with the Indian Institute of Technology at Kharagpur, and also Jadavpur University in Kolkata. And Anand, Professor Bhattacharya did mention this course, Fundamentals of Electronics Packaging, and but we're going to work on this course a bit more and bring in some of the advanced packaging technologies into the course and talk to industry as well to see how this course would be useful for industry participation. And this is funded by the British Council. So I would like to end my presentation there, and thank you everyone for listening. And if you have any questions, I'll be delighted to answer those. Thank you very much.
Thank you, Professor Bailey, and I believe everybody on this in the audience today enjoyed your presentation and learned, and more importantly, learned a lot. I think the way the advanced manufacturing, the advanced package design, as well as additive manufacturing are coming together today to give us immense possibilities was extremely enlightening for all of us. So there are a few questions on the chat box. I would probably just like to start with asking you that if you can elaborate a little more on the 3D stacking and 3D packaging or integrated packages that we have today, and what kind of devices are being used for 3D packaging? Is it like CPU, memory stacked on top, or mostly are they packages, or are they chips of similar architecture?
Similar. It's the biggest market, Anand, for this is, and you would see a lot of Samsung type packages. It's memory, stacking of memory. The challenge with placing a logic die in that stack, although this is starting to happen, but it's the heat removal. So how do we remove the heat from that's generated mainly from the active die or the logic die through a stack like that? So there's a lot of research in that area, but the main technologies used for stacking today, and I'm talking about 8, 9, 12 die stacked on top of each other, is traditionally memory technology.
Okay, wonderful. Okay. I had was regarding you did mention that there has been a shift to move from this move. So you maybe in a couple of sentences, just at the place today, are we close to finding an optimized alternate lead-free solder composition, or are there still multiple formulations that are being tried out?
The most traditional, or the main lead-free solder used today in the consumer electronics market for sure is tin, silver, copper, what we call SAC 305. I did show an example above of where indium solder was used for a focal plane array, and that's because that would go into some very cold environments. So the solder that you would use depends on the environment you're placing that solder in and the reliability. But generally today, the main solder that you used is tin, silver, copper. So there's no lead. But there's many patents out there on different solders that are lead-free. So it's quite a big area.
Yep.
But the most popular one is SAC, tin, silver, copper.
Thank you. Yeah, sure. I believe a lot of these, even the properties and their performances under different thermomechanical stresses, have to be all re-evaluated towards the most optimal composition.
Yes,
so
and it's huge amounts of. I was just going to say, Anand, there's a huge amount of research in generating the creep data for these materials, and this is where metrology links very closely with modeling and simulation, because that creep data, I didn't go into much detail on the actual materials data that goes into models here, but that data needs to be accurate, so accurate creep data. And of course, we're looking at very small amounts of material here, so this is not traditional creep testing of bulk materials. You need to understand how to do creep testing of very small materials where microstructural effects may become quite important.
Yeah, wonderful. And I think some of the examples that you showed about, multi-physics modeling, and also what 3D packaging, 3D manufacturing can make possible, especially that fractal-based or topological designs of the heat sinks. Those were really fascinating, and I believe would be of a lot of interest to a lot of students who are on the forum today. Before I move on to the chat box, Professor Pal, would you have any questions for Professor Bailey?
No, yeah, please go ahead. Yeah, it's fine. Yeah.
Okay. Okay, thank you. Yeah. So the first question is from Sambhav. He's a student. I know him in my department. He's asking, how is the thermal taken care of in 3D packages, 3D ICs?
In 3D ICs, generally you're looking for materials with high thermal conductivity, but you're trying to match the CTE. So when you look at these materials, a good thermal conductivity, that's great. You can start spreading the heat, but you need to be careful of the CTE mismatch in the choice of those materials, because that generates stress. Now, there is quite a lot of work in both passive cooling technologies, and what I mean by passive is that's generally based on thermal conductivity, and also active cooling. So where you can now start building in microchannels, where you can now start pumping fluids through this, or have a fluid type system where you can get much greater heat transfer using active cooling technologies. So it's a very good question. There are a number of technologies that can be used in the domain of passive or active. And then, of course, having that stack and a heat sink on top of that is another traditional method that would be used.
Absolutely, yeah. The next question is that is it possible to use low-cost FDM type additive manufacturing processes in future for making electronics packages?
Yes. I took this slide out, and let me, if you Google Voxel 8, VOXEL and the number 8, this is from, I think it was a university in the US, but they did produce a low-cost FDM type printer. When I say low cost, I think it was about $8,000. But it could do 3D printing of tracks, conductive tracks on a substrate, and placement of components on that. Of course, the resolution of the tracks was quite crude, but it was a low-cost example of seeing how 3D printing could be used in fabricating electronic component systems. So Voxel, yep. So there is some low-cost ones, which are good for the university lab, and there's things you can do there. One of the challenges with 3D printing is the conductive materials and getting the electrical properties that you would also find in traditional printed circuit boards. So because you're printing here a paste, and then you would sinter that paste. So getting those properties, but lots of research going on there. But the high-end printers like the Nano Dimension are very expensive, of course. That's the other end. But you do have these low-cost ones as well, and the one I was thinking of is Voxel 8.
Thank you. There's another question which is a little generic. That the question is about what are the current trends about original theoretical research that is being done towards packaging and failure analysis in academia, either in UK or worldwide? What are some of the thrust areas or key areas where there is focus?
And this is focus, sorry, Anand, it's in packaging and failure analysis.
Yeah, theoretical research.
Yeah. Theoretical research. With regards theoretical research, there's a huge amount of research taking place in understanding reliability and physics of failure type of analysis and the calculations and predictions for that. So quite a lot of work in that space. And then I did mention this whole area of machine learning algorithms.
Yes.
How do you use those effectively with the data, and what data should you use? Because in manufacturing today, it's not a new term; it's been around for a while. But Industry 4.0, gathering data through the Internet of Things, lots of sensors, but also the data we've traditionally gathered through qualification and reliability testing. How do you use all this data? What theoretical techniques do you use to analyze this data to generate knowledge that enables productivity in industry?
Yeah, I think that was quite an eye-opener for many of us. I think when you showed how machine learning was used to look at the reliability of two similar packages.
Yes.
Two similar. That's right.
Yeah, and the company there, Anand, that I was working with, I remember the manager said to me that, Chris, we've been collecting this data for 20 years, and we have to collect it, we have to store it because it's a customer requirement. But is there any knowledge in this data? So many different package types that have been assessed, all of this. And the question was that when we get a new package, we have to go through all of this assessment process. And it would be really interesting to know how similar this package architecture and its behavior would be to one that we did in the past, because the knowledge is there. So understanding that similarity between a new package and one that's been done in the past can really enable productivity and save costs.
Yeah, that's excellent. And I believe this is somewhere academic research and academics working closely with industries can make a very formidable impact.
Yeah.
There's another question from a student. Again, I know him, Sambhav, that is there any advancement in wafer fabrication from Czochralski process? I mean, other than Czochralski process. And he's a second part of question, which is unrelated. His question is, he wants to know what pixel array means because that's a new term to him. Anyway, these are two different questions.
The wafer process, the Czochralski process is actually how you grow. If I remember correctly, this is how you grow a wafer. Yeah, it's the whole wafer ingot. I think that's a well-established process. There's obviously different parameters that you may use. Obviously, we're moving towards today different types of material. This whole area of compound semiconductors, and particularly gallium nitride and silicon carbide. So I think there's a lot of interest there and technology developments in how these are built up. But generally, with the traditional process, it's not my area that I've worked in, but I think that's quite well established. You grow that single crystal, and then you essentially solidify this and create the whole ingot. But I think if you look at the new semiconductor materials, I say new, the compound semiconductor materials, there's huge interest in this in the UK. And how do we optimize their behavior and their design? That's a big area for the device community.
Yeah, that's true. Absolutely. We had a visiting professor here and who was actually looking into how how to grow wafers with gallium nitride.
Yeah. Oh, sorry, there was a
Okay.
second question.
Second question was, what is a pixel array?
Oh, a pixel array. This is it's essentially many pixels on the device, and it's essentially picking up images. So that example. So it's optical. But you would then transmit that data into a silicon readout, so that optical to electrical connection. That example there, that focal plane array, and those pixels that would be there, but every one of those would have an interconnect going down to a readout chip.
Yep. Okay. The next question is, how can we detect the random damages that may occur during manufacturing of 3D printed miniaturized components?
It's understanding. Now, this is the area of condition monitoring, and it's we're all used to statistical process control, where we're monitoring certain parameters and understanding the variation in those parameters, and we can relate that back to quality of a fabricated part. But understanding failure, where failure may be occurring, you need to be able to understand what you can measure that would relate to a particular failure. So this is the whole area of condition monitoring, which is a very exciting area today because of the whole industry 4.0 and gathering data from our assembly, the whole board assembly, as well as when the product's in the field, and understanding how it behaves there and monitoring its behavior. So in high reliability applications, this is a very important area, but this is condition monitoring, which is again about certain mathematical models, and also what's known as prognostics and health management of the system. And we have that in our cars today. There's certain red lights will come on to say, there's something going wrong here, but it's monitoring some data from that, and it knows when that data value reaches a certain critical value that something is not right. So understanding failures in an assembly line and in the manufacturing process, you need to understand what you're monitoring in the data and then relate that to the failure. So there's many ways of gathering that data, whether it's through sensors or vision equipment. But we are today, and that's the example I gave earlier, huge amounts of data is now becoming available. It's how we use that data to generate knowledge.
Yeah. No, and you also did show an example where there was, after the fabrication, there was an inspection table where I believe you try to monitor some properties to make sure that there are no defects.
Yeah, Anandaroop, I'd like to ask one question over here.
Yes, please.
Yeah. So Professor Bailey, you mentioned about the machine learning, the approach for finding out the more data and prediction model and all. I understand that for validation purpose, you need to have the performance test. So, you are gathering data from the manufacturing stations, one stations to the other stations. But how do you get the data for the validation performance of the component on that?
What's a very interesting area today is how you combine simulation data. So above you would have seen numerous simulations predicting the performance. So you can now combine simulation data with measured data, and then use either supervised or unsupervised learning type machine learning algorithms to assess that data, to do the correlations, the classification, and that sort of thing. But your question, really, it's about combining measured data, and where there's gaps in the data, using simulation to add value to the data. Of course, you need accurate simulations, but you're merging data from simulation and real measured data.
I think we are already past 9:30, maybe one question. This is also from student Jas. So he's asking that, yeah, of course, the multiphysics and co-design that you talked about was extremely enlightening. And he's asking his question is, can you discuss more on the integration of mechanical and electrical design? I mean, how can both be simultaneously accomplished? And does it call for a fundamental change in the design thinking itself? I think it's a very interesting question. The co-design part, you can, I would really like to hear from you.
Well, if you think about electrical design, we're looking and we're very interested in signal integrity, power integrity, and also electromagnetic interference in certain products, so that electromagnetic field. And for an electrical designer, they can optimize that by a certain layout and architecture. But generally, when that goes to a thermal designer, they would want to change it again because it's not too good for thermal. And thermal, of course, drives mechanical generally. So you have this link because the electrical design, you're going to get dual heating effects, switching losses in power devices. So you're generating heat in the electrical domain. But you're designing this to minimize the effects of EMI and also optimize power and signal integrity. But that design may not work because you don't have the integrated design flows for thermal and mechanical. So this is where the design space or the design tools need to work collaboratively. But also you do have electrical mechanical interactions, and in particular I showed that which is a real challenge today with some of these very tiny interconnects, these the metal migration due to high current densities, but it's a thermal and mechanical problem as well. So those are the students here who may remember their partial differential equations. You know, some of these partial differential equations are coupled. So you, from the electrical, dual heating it's a source term that goes into the thermal equation. And tools like ANSYS or COMSOL will actually solve these interactions. But, you know, we need the right data and we need the right design environments to do this sort of electrical to mechanical integration in the design space, and thermal is in the middle.
Yeah, that's actually I may want to mention that it has been 3 years. I don't know. In 2019, I went to this European conference, Therminic, and I saw that the focus, especially among European academia, on this what they were calling electrothermal modeling, which is electrical and thermal, coupled modeling. It was it was just coincidental that my paper was on something called electrothermal flows, which is completely different, how to give rise to flow under electrical AC electric field. And when I went up, they thought that I'm going to talk about something like electrothermal modeling. I had to first tell them this electrothermal is completely different from what we have been theorizing. Okay. I think that's pretty much. There are some comments. Otherwise, I think Srinivas, you mentioned about ComSol, which was a Bailey also mentioned, and many of our students use it. Others, there are some comments and views. I believe if there's no other questions from anyone else, I believe I will hand it over to Professor Pal to bring this session to a close.
Yeah. Thank you. Thank you, Professor Bailey, for your wonderful talk. I think everybody has enjoyed a lot and would be interested to work with you, collaborate with you in future. Thank you, Anandaroop, for your nice moderation. And with this, we'd like to close today's.
I would just like to mention that Professor Bailey, especially for the students and all the people on IIT Kharagpur, Professor Bailey will be here hopefully sometime in March. hopefully we won't have another wave, so everything will be smooth from here onwards. So if that happens, he will be here next month, and we will get a chance to meet him face to face and have a lot more discussions like these.
Yeah, that will be a wonderful experience. So the students can also interact. Yeah, so with this, I'd like to close today's session, and I request Ananta to let us know about the speakers for the next weeks. Yeah, thank you, Professor, for your presentation today.
Thank you, everyone, and I look forward to seeing you all soon. Thank you.
The next week, that is on February 19th, the speaker would be Dr. Bhattacharya Mandal. He'll be talking about the process modeling and its importance in manufacturing. Dr. Mandal is from the University of Manchester in the UK. Next to next week would be the Professor Sujit Banerjee from Warwick Manufacturing Group. He would be talking about the evolution of cloud computing and its importance in manufacturing. You can all watch our previous videos, webinars, to capturing this the code. Thank you so much.